Dear students, welcome to all of you. Now we discuss 2023 Biomathematics question paper DSE A 1.2, Group B, Unit 1, Semester 5, Mathematics Honors under CBCS, University of Calcutta. Question paper 2023 Biomathematics, Group B, Unit 1. Question 2A. What is meant by Allee effect? Consider the growth model ddt of n equal to Rn bracket n by a minus 1 bracket close into bracket 1 minus n by k bracket close, where R, A, K are positive parameters and a less than k. Determine the steady states and discuss their stability. First part, Allee effect. The logistic growth model is given by ddt of n equal to alpha n bracket 1 minus n by k bracket close. Equation 1, parameters alpha and k are positive parameters, shows that the per capita growth rate, that is 1 by n ddt of n, is positive up to the population density nt attains the carrying capacity k of the environment for the population. But in the real world, we observe that the per capita growth rate becomes negative at low population density due to unavailability of mates or lack of cooperative behaviors, etc. This phenomenon is known as the Allee effect. This is the graph, this n versus 1 by n dn dt is for this logistic model. Here, no Allee effect. This is the K carrying capacity. So when n equal to 0, put here when n equal to 0, then this 1 by n, 1 by n equal to 0, 1 by n dn dt equal to alpha. So value is alpha. When n equal to k, when n equal to k, this 1 minus k by k, that is 1. So 1 by n dn dt equal to 0. So this is. So 1 by n dn dt, that is per capita growth rate for logistic model, is always positive for population size. But for the model of Allee effect, this growth model for Allee effect, 1 by n dn dt, that is equal to R bracket n by a minus 1 into bracket 1 minus n by k. So when n equal to 0, when n equal to 0, this minus R, actually this is the alpha model. Here we consider R, here is alpha, and alpha and R are same. So you can consider this, actually this R. So according to this model, you can consider this R, and so you can consider this R, this. So this is equals to R. And when this n equal to A, n equal to A, so A by A, this 1 minus 1, 0. So 1 by n dn dt, 1 by n dn dt equal to 0. And when n equal to k, this 1 minus 1, this also 0. So 1 by n dn dt is also 0. So 1 by n dn dt, that is per capita growth rate for model of Allee effect, this when n is very small, then 1 by n dn dt and negative here. But the logistic model, 1 by n dn dt is always positive. Next question, second part. Consider the growth model this and determine the steady states and discuss their stability. So dn dt equal to this equal to fn say, where E is the Allee threshold, and then fn equal to this function, R positive and A lies between 0 and k, Allee threshold lies between 0 and k. To find the steady states, if n star be steady state, then fn star equal to 0. So put n star here, or n star bracket n star by minus a by a minus 1 into 1 minus n star by k equal to 0. So n star equal to 0, n2 star equal to a, or n3 star equal to k. So there are three steady states here. This is the trivial steady states, and this n2 star equal to a and n3 star equal to k are non-trivial steady states. Now, the stability analysis of these steady states, I find f dash in. So if n equal to this, find f dash in. So you get r bracket n by a minus 1 into bracket 1 minus n by k plus n into 1 by a into 1 minus n by k plus n into minus 1 by k into bracket n by a minus 1. So we find f dash 0 or first steady state, non-trivial steady state, or trivial steady state. F dash equal to f dash 0 equal to put n equal to 0. So this term 0, this term 0. So n equal to 0. So this is minus r, and r is positive growth rate. So this negative. So 0, that is the trivial steady state. N1 star is asymptotically stable steady state. Next, second steady state, n2 star equal to a, f dash a equal to r into 1 minus a by k. This is a by a minus 1. So this term is 0. So this greater than 0 because 0 less than a less than k. So a by k is less than 1. So obviously this f dash a, this value is positive. So steady state n2 star equal to a is unstable. And f dash k equal to r into bracket 1 minus k by a. This is less than 0 because k by a is greater than 1. So this is less than 0. Hence, steady state n3 star k equal n3 star equal to k is asymptotically stable steady state. Next, this question, I discuss the stability. Next question, 2b. Discuss the stability of the steady states of the following harvesting model. Dt n equal to r in bracket 1 minus n by k minus h for the cases h less than equal to or greater than rk by 4, where r greater than 0 is the growth rate, h greater than 0 is the constant rate of harvesting, and k greater than 0 is the carrying capacity of the environment of this model. Given model is this, let fn equal to this rn into bracket 1 minus n by k minus h. To find steady states, if n star be a steady state, then fn star equal to 0. So rn star into bracket 1 minus n star by k minus h equal to 0. So we get this quadratic in n star. So n star square minus k n star plus k h by r is equal to 0. The discriminant of this quadratic equation is b square minus 4ac. So k square minus 4 a into c is 1, c is k h by r is equal to 4k by r into bracket rk by 4 minus h. Then there are two steady states, n1 star and n2 star. This is equal to this minus b, that is minus k, plus minus root over b square minus 4c, that is discriminant d, whole divided by 2 into A is 1. So K plus minus root over D by 2. If case 1, if discriminant D is positive, so Rk by 4 minus H is greater than 0, that is Rk by 4 is greater than H. Then the given model has two steady states. This A1 star, that is K minus root over D whole divided by 2, and N2 star equal to K plus root over D whole divided by 2. Now, Fn equal to this Fn equal to this Rn into bracket 1 minus N by K minus H, and F dash n equal to R minus 2Rn by K. H is constant. So this equal to R common into 1 minus 2n by K. Equation 3. So F dash n1 star is equal to R into bracket 1 minus 2n1 star by K. Is equal to R minus 2R by K into n1 star. And value of n1 star is K minus root over D by 2 whole divided by 2. So after simplification, we get R root over D by K. This D is greater than 0, this case, and K is carrying capacity greater than 0, R is growth rate greater than 0. So this F dash n1 star is greater than 0. Hence, n1 star equal to K minus root over D whole divided by 2 is unstable, is an unstable steady state. Again, F dash n2 star, this equal to, after simplification, we get minus R root over D by K. Obviously, this is negative. So this n2 star is asymptotically stable steady state. Case 2, if D equal to 0, discriminant equal to 0, so if Rk by 4 equal to H, then we have only one steady state, N star equal to K by 2. Obviously, this D equal to 0, so N1 star equal to N2 star equal to N star, that is equal to K by 2. And if dash N star is equal to R minus 2R by K N star K by 2 is equal to 0. So stability of N star cannot be determined by the sign convention. That means by linearization technique, we can find the stability of this N star by geometrical method. So not discussed here. And case 3, if D less than 0, that is if H is greater than Rk by 4, then those two steady states N1 star and N2 star are complex numbers, because this discriminant is negative. So root over of negative quantity, obviously this is the complex number. This is the complex number. So there is no steady states in this case. Next question, 2C. Suppose that a population follows Malthus growth model. If it has 24 into 10 to the power 5 members after 5 years and 15 to 10 to the power 5 members after 15 years, what was the initial population size? March 3. The Malthusian population model is given by GD of n equal to alpha into n. Alpha is the growth rate, is the population size at any time t. So this alpha, that is equal to 1 by n dndt, that is the per capita growth rate. This alpha is positive here. Solution of 1, we know the solution of 1, this nt equal to n0 e to the power alpha t. So called this is the exponential model. Here n0, the initial population size when t equal to time t equal to 0. From the given data, we have n5 equal to 24 into 10 to the power 5, because this n equal to this after 5 years. So here t unit is year. So this n5 equal to this, and this 15 into 10 to the power 5 members after 15 years. So n15 equal to this. So we get from 2, this n0 to the power 5 alpha equal to this, and n0 to the power 15 alpha equal to this. So from this, we can write this e to the power 5 alpha whole to the power 3. Now, e to the power 5 alpha equal to 24 into 10 to the power 5 by n0. From this first equation. So this n0 and this n0 cube. So divided by n0 square. So value of n0 square is this. So n0 equal to square root of this equal to 24 root over 8 by 5 into 10 to the power 5 equal to approximately equal to 30.36 into 10 to the power 5. Hence the initial population size, that is n0, is this 30.36 into 10 to the power 5. Required answer. Next question, 3a. What is meant by bifurcation? Discuss the saddle node bifurcation for the system dxdt equal to mu plus x square. Mu belongs to real number, where mu is a parameter. A bifurcation occurs in a nonlinear dynamical system dxdt equal to fx mu, where mu is a parameter. When a small change in the parameter mu results in a qualitative change in trajectory structure of the system, the system is said to have a bifurcation at mu equal to mu c, particular value of mu, this mu c, if there is a change in the number of steady states and or in stability behaviors of the steady states. That means from stable, asymptotically stable to unstable, or unstable to asymptotically stable, when mu crosses the value mu c. Next, we discuss the saddle node bifurcation for this system. Obviously, this system, nonlinear dynamical system, this x square is the dependent variable, this square, so is the nonlinear first order differential equation. Ddt of x equal to mu plus x square. This mu plus x equal to fxa, where fx equal to mu plus x square, and for steady states x star, fx star equal to 0. And so x1 star and x2 star equal to plus minus root over of minus mu. And f dash x, this is equal to 2x. So f dash x1 star, this is equal to 2x1 star, that is equal to minus 2 into root over of minus mu. And f dash x2 star equal to 2 root over minus mu. Case 1, if mu is negative, so when mu is negative, so this this quantity under this square root is positive quantity. So obviously this quantity is whole quantity is negative. So x1 star equal to minus root over minus mu is asymptotically stable. And f dash x2 star is positive. So this x2 star equal to root over of minus mu is unstable, steady states. Case 2, if mu equal to 0. So so we have only one steady state, x star equal to 0. Since f dash x star is equal to 2 into 0, this 0. So we cannot decide about stability at x star equal to 0 from sign convention, that is by linearization technique. And by graphical method, we can show this x star equal to 0 is a semi-stable steady state. If we draw this graph by Desmos application, we can draw this page portrait for mu negative, this x1 star, this solid circle, this x1 star, this is stable, and this x2 star unstable. So hollow circle here, and this arrow away from this point, and this portion is solid and this portion is hollow, because this side is stable and this side is unstable, away from this and this towards this point. So this is semi-stable for mu equal to 0. And if mu greater than 0, then this x1 star and x2 star are purely complex numbers. So we cannot find any steady states. And this corresponding bifurcation diagram, this when this mu and x, when mu is negative, we get this point x2 star, and this x2 star is unstable. So we write this positive quantity, a positive value, x2 star is positive. So this dotted line, this unstable uh, branch, and x1 star is negative. So x1 star is negative, and this is the um, continuous curve runs this table. So arrow towards this point and this arrow away from these points. So this unstable. Okay. And this bifurcation is known as subcritical saddle node bifurcation. And this point and bifurcation point is 0. This bifurcation point is 0. So this is the bifurcation diagram for this. Next question, question 3b. So by using transformation, capital N equal to AX, capital T equal to AT by M, the following Rolls-Barrow model, D capital N in D capital T equal to R in bracket 1 minus N by K minus Mn square whole divided by A square minus N square, where the symbols have their usual meanings, can be put in the following dimensionless form. Dx dt this equal to px bracket 1 minus x by q minus x square by 1 plus x square, where the constants p and q are to be determined by you. Also discuss the stability of the trivial steady state. Here, this variable capital N equal to ax and capital T equal to a small t by m. So x equal to capital N by A and small t equal to m by A into capital T. So obviously dx equal to 1 by n and d capital N and dt equal to m by A d capital T. So ddt of x is equal to, so put dx equal to 1 by A dn and this dt equal to m by A dt. So this 1 by m and this dn by dt equal to this r in bracket 1 minus n by k. So r in, value of capital N is ax, put here ax, and bracket 1 minus n by k. N is the ax and k, and bracket close, minus m into a square x square whole divided by a square plus a square x square. So after simplification, we get this, and ddt of x equal to this quantity is p, x bracket into bracket 1 minus x by q bracket close minus x square by 1 minus 1 plus x square, equation 1, where p equal to ra by m and q equal to k, capital K by a. The equation 1 is the required dimensionless form of the given equation. Next question, and also discuss the stability of the trivial steady state, that is x star equal to 0. Let dx dt equal to fx. So fx equals to this px into bracket 1 minus x by q minus x square whole divided by 1 plus x square. Obviously, this if x star equal to 0 gives x star equal to 0. So x star is a steady state. Actually, this is the trivial steady state. And f dash x equal to this p into bracket 1 minus 2x by q bracket close minus 2x into bracket 1 plus x square bracket close minus 2x into x square whole divided by 1 plus x square whole square. Now f dash 0 for this trivial steady state, put x equal to 0 here. So only p. This p is greater than 0 because p equal to ra by m, r positive, a positive, m positive. So obviously this quantity is positive. Hence, the trivial steady state x star equal to 0 is unstable steady state. Is an unstable steady state. Next question, 3c. Question 3c. For the logistic model, ddt of x equal to rx into bracket 1 minus x by capital K, bracket close, with x0 less than k capital K by 2, where the symbols have their usual meanings, so that x equal to k is an asymptotically stable steady state. Also show that the solution curve has a point of inflection at x equal to k by 2. Hence, draw the rough sketch of the solution curve. Number two solution 2 plus 2 plus 1. We have the logistic model, derivative of x equal to rx into bracket 1 minus x by capital T. Let derivative of x equal to fx, where fx equals to rx into bracket 1 minus x by capital T. Then f dash x equal to r into bracket 1 minus 2x by capital T. Now, for steady state x star, if x star equal to 0 implies r x star into bracket 1 minus x star by k equal to 0. Hence, x1 star equal to 0 and x2 star equal to k. There are two steady states. We have to find this k for x equal to k asymptotically stable steady state. So we want to discuss the stability nature for this non-trivial steady state. So f dash k equal to r into bracket 1 minus 2k by k, that is equal to minus r, this less than 0 because r is positive in growth rate. So x2 star equal to k is an asymptotically stable steady state. Here, k is the carrying capacity of the environment for this model. Second part, also show that the solution curve has a point of inflection at the point x equal to k by 2. Now, d2 dt square of x equal to ddx of rx into bracket 1 minus x by k into ddt of x. Now, this r x, so r, this x square, so 2x into this, and ddt of x equal to this ddt of x equals to rx into bracket 1 minus x by k. So put this value of ddt of x equal to this. So r square by k square, this k minus 2x into k minus x into x. Now, d2x dt square equal to 0 implies this x equal to k by 2 and x equal to k, but x not equal to k because this carrying capacity k, this x is less than k. So d2x dt square is positive when these two factors both are positive and both are negative. So x is always positive here. So this k minus 2x is positive and k minus x is positive. That is, x is less than k by 2 and x is less than k. That is, x is less than k by 2 and x is less than k. So combinedly, we can find x is less than k by 2. d2x dt square positive. In another case, d2x dt square positive when both factors are negative. That is, k minus 2x is negative and k minus x is negative. So x is greater than k by 2 and x is greater than k, but x is always less than k. So it is impossible case. It is an impossible case. And d2x dt square is negative when uh, opposite signs, these two factors are opposite signs, either this positive, this negative, or this positive. So first case, k minus 2x is positive and k minus x is negative. So this x is less than k by 2 and x is greater than k by 2. X is less than k by 2 is this region and x is greater than k is this region. So it is absurd. So this is an impossible case. Or another case, d2x dt square is negative. This first factor k minus 2x is negative and k minus x is positive. That is, x is greater than k by 2, x is less than k. So x is greater than k by 2 and x is less than k. So actually k by 2 less than x less than k. So sum up this result. d2x dt square is greater than 0 when x is less than k by 2, d2x dt square equal to 0 when x equal to k by 2, and d2x dt square is less than 0 when k by 2 less than x less than k. Thus, for this interval 0 less than x less than k by 2, this second derivative of x with respect to t is positive, that is ddt of x is an increasing function of t, and so xt is concave upwards. So xt is an concave upwards. So this is the concave upwards. And for this region k by 2 less than x less than k, and d2 of dt square is negative, d2x dt square is negative, and so ddt of x is decreasing function of t, and so xt is concave downwards. So this is xt is concave downwards in this region. Thus, concavity of this solution curve, this is the solution curve, actually this is the time axis, and this is the population size xt, and this carrying capacity k, and this point is k by 2, and this initial population x0, and this origin 0. So the solution curve, concavity of the solution curve, and this is the concave from outwards, from upwards, and this is the concave from downwards. So have a point of inflection at this point k by 2, where this d2x and dt square equal to 0 at this point. And so xt grows fastest when x equal to k by 2. Thank you. This completes Unit 1, 2023 Biomathematics. Thank you for watching this video.